Good morning, students. So let's study today chapter hydrogen. You know, children, that hydrogen is the first element of periodic table. It is the lightest element of periodic table with atomic number 1. How do you write the electronic configuration of it? So you can see on the screen, its electronic configuration is 1s1. Meaning of 1 is here, principal quantum number, value is 1, means K shell, and S stands for S orbital, which is filled with only one electron. On one hand, its electronic configuration is similar to the outer electronic configuration, that is NS1 of alkali metals. On the other hand, like halogens with NS2 and P5 configuration belonging to the 17th group of periodic table. That means in case of halogen, where you are seeing the configuration is NS2 and P5 requires only one electron to complete its octet or to get the stability. It means valency of alkali metals and halogens are 1, that is same as valency of hydrogen. So we can say here hydrogen therefore has resemblance to alkali metals which lose one electron to form unipositive ions, as well as with halogens which gain one electron to form uni-negative ion. Now look at this hydrides I'm presenting here. First I'll tell you the meaning of hydride. These the compounds you're seeing on the screen are the compounds of hydrogen with other elements. Like the first yellow two groups you're seeing here are hydrides of alkali metals. These are lithium hydride, sodium hydride, potassium hydride, rubidium hydride and cesium hydride. And the hydrides of alkaline earth metals. Here are beryllium hydride, magnesium hydride, calcium hydride, strontium hydride and barium hydride. Not only these alkali and alkaline earth metal hydrides are here on your screen, but also you can see in the red box. These are the hydrides of group 13 elements boron family. And these are named as boron hydride, aluminium hydride, gallium hydride and indium hydride. Okay? And the rest purple and the blue boxes you are seeing, these are hydrides of all P block elements of group 14, group 15, group 16 and group 17. Now, as I am telling you about the hydrides, let's study that how many types of hydrides are there. So as I told you students, dihydrogen under certain conditions combines with almost all the elements as you seen in the previous slide except noble gases to form binary compounds called hydrides. And if you want to write the general formula of hydrides, we can write HX. Okay, now how we can classify hydrides? So classification of hydrides can be done in 3 categories. First one is ionic or saline or also known as salt-like hydrides. Second one is covalent or molecular hydrides. And third one is metallic or non-stoichiometric hydrides. Now let us study these hydrides one by one. First one is ionic or salt-like hydrides. So let us go for some of its properties, or I would say characteristic properties or features. First one is these are stoichiometric hydrides. Stoichiometry means it has fixed composition. And of course, these are compounds of dihydrogen. Second one, these are formed by highly electropositive S block elements and dihydrogen. S block elements means alkali metals and alkaline earth metals, which you have seen already in previous slide. Third property is these hydrides are ionic, crystalline, non-volatile and non-conducting in solid state. And the last one is their melts means in their molten state, and aqueous solution, it means their solution in water, are good conductor of electricity. You know the reason, you have studied in previous chapters. When ionic compound is in molten state or in its aqueous medium, its ion become free or ion gets mobile. When ion get freed, it is capable to carry current from one place to another. Now look here in this slide, the picture is clearly showing here that what is the arrangement and how these hydride ion and alkali metal cation arranges itself in its lattice. So right hand side, the lattice, 3D lattice is shown here with purple balls and white balls, which are representing the two ions arrangement in the lattice. And left side you can see the electronic configuration of sodium cation. The configuration showing 2 electrons present in K shell and 8 electrons present in L shell. And one of the electron or valence electron of the outermost shell is lost by sodium. So sodium has converted into sodium cation. Beside it, you can see H, the ball H you are seeing, yellow color ball. Having only one shell, that is K shell. And now the configuration of hydrogen has become 1s2 because it has gained one of the electron from sodium. Okay, so this is sodium hydride, one of the ionic hydride that is formed between alkali metal sodium and non-metal hydrogen. Now, next type of hydride is covalent or the molecular hydride. Now let's see the features. Dihydrogen forms molecular compounds with most of the p block elements. You know, p block elements are right from group number 13 as I shown in the previous slide to group number 17. Molecular hydrides are further classified according to the relative numbers of electrons and bonds. First one is electron deficient covalent hydride. Second one, electron precise covalent or molecular hydride. And third one is electron rich covalent or molecular hydride. Now look at the examples of covalent hydrides. So first I told you students, electron deficient hydride. So first example, right to the left corner you are seeing of boron hydride, BH3. Have a look on the Lewis dot structure of BH3. Even after the formation of 3 bonds with hydrogen, boron as central element is unable to complete its octet. It means this hydride is electron deficient covalent hydride. Second type I told you, electron precise hydride. Now have a look to the right hand side of CH4 dot structure. Here you can see clearly that carbon is forming 4 bonds with hydrogen. And after the formation of 4 bond, not only hydrogen complete its duplet but also carbon have completed its octet. And you can find here that neither electrons are required nor left over after the bond formation. So such type of hydrides are known as electron precise covalent hydride. Now look at the lower picture of pH3. This is phosphine. By the name it is phosphine. Otherwise I would say this is hydride of phosphorus. And it is electron rich hydride. Now why I am calling it electron rich? So see here students that when phosphorus forms 3 bond with hydrogen, hydrogen has completed its duplet and phosphorus not only complete its octet but a lone pair of electron or say unshared pair of electron is also left out. This presence of unshared pair of electron makes pH3 electron rich hydride. And for your information, I should inform you here, as you have seen already in previous slide, that boron belongs to group number 13, carbon belongs to group number 14, and phosphorus belongs to group number 15. Now, let's see metallic or non-stoichiometric hydrides. These are the hydrides formed by many D block and F block elements. Here many means not by all. See, metals of group number 7, 8 and 9 do not form hydride. And this is known as hydride gap. In these hydrides, hydrogen occupies voids or interstitial spaces in the metal lattice. Now what's the meaning of voids or interstitial spaces here? So you have studied already in previous topics that void means the hole or the space which is left out in crystal lattice. Here you can see the example of these metallic or the non-stoichiometric hydrides. Examples are lanthanum hydrides. You see the ratio of lanthanum and hydrogen is not exactly 1:1, but it is more than 1. It means composition of lanthanum hydride is not equal to the theoretical calculation, but it varies. That's why these metallic hydrides are known as non-stoichiometric, means with varying composition hydrides. One more example I gave you here is zirconium hydride, where the composition of hydride is not exactly equals to 1 as this should be, but it is 1.3 to 1.75. So this is about metallic or the non-stoichiometric hydrides. Now have a look at the image of this metallic hydride, which is non-stoichiometric hydride. You're seeing here, I'm showing you clearly that the blue small balls are actually representing small sized hydrogen atoms. And these grey big balls are actually representing lattice of transition metal. Since the gap or the void which is available here are of sufficient big size where hydrogen atom can occupy itself. So these voids are the interstitial spaces occupied by small sized hydrogen, and this becomes non-stoichiometric or interstitial or metallic hydrides. Thank you everyone.